what I want to do today is to go and explain a little bit more about this concept of bounded charge and what does it mean when we're talking about a surface bounded charge and a volumetric bounded charge. And also want to talk a little bit more about what is the difference that happens when we have a conductor inside an electric field versus a dielectric. And right now we're talking about dielectrics. We're going to talk about conductors later on. But we talked about this earlier, the last couple of weeks. So imagine that we have a conductor, some metallic slab. And we're going to have this electric field going into the conductor or flying through the conductor. So as the free charges that exist in the conductor starts perceiving the electric field, basically what's going to happen is that some of these free charges are going to kind of move closer to the electric field. So we're going to have a bunch of negative charges over here. And then because of on the other side, we're going to have a bunch of positive charges. Okay, and what happens inside is that we're going to have an electric field that opposes the external electric field. And as a consequence, what happened is that we have this external electric field, and it's going to be equals to the internal electric field. So the net effect is that inside the conductor, the electric field is going to be zero. Okay, and that happens because the charges are free to move, and then they can move anywhere they are. So you can have these really high accumulations of charges on one side of the conductors or not. Now, when we work with dielectrics, is something similar happen, but it's not as efficient. So when you have a dielectric, we have your slab of dielectric. And imagine this electric, you're going to have these little molecules with positive and negative charges. So they're electrical neutral, but you're going to have these little molecules with plus and minus, and they're going to be random oriented. You're going to do this bigger because otherwise you're going to, guys, not going to be able to see. Okay, and when you experience, and when you have an electric field going through this material, what's going to happen is that these molecules are going to kind of orient themselves along the electric field. And I'm going to exaggerate this here, but imagine that you have something like this. I should have done it bigger. We have plus, minus, no, minus, plus, minus, plus. Yeah, something like that. So I have my electric field. Okay, and inside the electric field, now all my molecules are going to be kind of oriented themselves to this electric field. Now notice that here in the volume inside my dielectric, I'm going to have this positive charge next to the negative charge, and then here I have a positive charge next to another negative charge. So kind of like in the middle, kind of like they're going to cancel each other. Okay, and on one edge, I'm going to have these negative charges accumulated on one side, and on the other side, I have all the positive charges. Okay, so we still going to have an electric field inside this inside the dielectric, but the electric field is not going to be as intense as what we have it on the conductor. The electric field inside the dielectric is going to be a little bit smaller, but it's going to exist. It's not going to be completely zero. It's not going to this electric field created by the polarization is not going to be as big as the external electric field. Okay, so these surfaces, these charges that add at the surface, that's what we call the bounded surface charges. And the ones that are in this middle, that's what we call the volumetric, the bounded volume density charge. Okay, makes sense? So imagine that I have my material. I have an electric field that is going through it. Okay, we're talking about dielectric. And because of this effect of the dielectric, I'm going to have a surface charge over here. And I'm going to have another surface charge over here. Okay. Now imagine that I grab a cookie cutter and I make a hole right there in the center. Okay. So I'm not going to draw the field lines anymore, the electric field lines anymore. But I make a hole. Okay, so I have these surface charges over here. I'm going to have these charges over there. And this hole will be like me removing all these charges here in the center. Okay, so it means that here on the edge, I'm still going to have kind of like another surface charges. And here I'm going to have another bounded surface charges. Okay. Makes sense? We call them bounded because they're not free to move. You can imagine they kind of rotate, they can be displaced a little bit, they can stretch, but they're not, they cannot move a lot. Okay. If we increase the magnitude of this electric field, we make them really, really big. You can imagine that these dipoles, these molecules are going to kind of stretch themselves. So you have a negative and a positive. And if you keep stretching this a lot, they're going to break. They break that bond that joined them, and that's been basically when you have a charge. So when you are in the winter and you have your feet on the ground to walk on a barefoot on a carpet, and then you touch someone and you see that spark, or you feel that shock. Basically, what you have is you're breaking that bond on the air, and you have this conductor jumping from a dielectric, which is air. And we call that dielectric breakdown, electric breakdown. Okay, makes sense? Okay, so So something that is that happens, for example, when we have, let's say I have a dielectric, and inside the dielectric, I'm gonna say that I have a shell, and inside the electric I have a free charge Q. Okay, so this charge is gonna create an electric field. Okay, so I'm gonna have my electric field flying all over the place. So if this is a dielectric, then that means that I'm gonna have a surface charge here at the edge. And that means that I'm gonna have a surface charge on the outside surface. And in between, I'm gonna have a volumetric boundary charge. Okay, so what we want to find out is, okay, how is electric field? What is a new electric field? What happened? What is the difference of this electric field when it's in the presence of this dielectric material? Does it change? Does it becomes bigger? That's the one that is on free space, or it becomes smaller? What is the magnitude of the polarization? What is the effect of these bounded charges? But these two are not simple to calculate. What we know is that the total charge density is going to be equals to the free charge density plus the volumetric charge density. Okay, and all this is going to be equals to the divergence of epsilon naught E. Okay, I can solve for the free one, for the free charge density, and the free charge density is going to be this minus the volumetric charge density. Okay, I know that this guy over here is going to be negative the divergence of the polarization density. So I can rewrite this and this over here is my displacement, my electric displacement. That is a negative over here. Okay. Okay, so what does this equation mean? Okay, so this is Gauss law. And basically says Gauss law, when we are calculating the electric displacement only gonna be dependent on the free charge. Okay, it's only gonna depend on the charge that we have inside our Gaussian surface. It's not gonna be affected by the polarization. It's not gonna be affected by the bounded charges. Okay, this electric displacement only depends on free charge. So calculating the electric displacement is relatively easy because it's the same way that we've been doing it so far. The only thing that we need to consider now is that it's going to be inside a different material. Once we have the electric displacement, then calculating the electric field is relatively easy. We just need to divide by epsilon. Okay, and once you have the electric field and the displacement, then the polarization is just going to be the displacement minus epsilon naught, the electric field. Okay. So some of the problems that we did on the last couple of classes, we were working with trying to find out the electric displacement and the polarization and the electric field on different situations. But we haven't really calculated the boundary charges. So let me go back to one problem that we were working on last class. Okay, so we have a dielectric sphere. On the dielectric sphere, it's a material epsilon r, and it has a volumetric charge density, a constant charge density rho. And what we did was to calculate the electric field, and we calculated the electric potential everywhere. We calculated the electric displacement, D, and we found a D for the outside, and we calculated the electric displacement. We calculated D on the in the inside, and then once we have that, we can calculate electric displacement. Okay, we can calculate then the polarization. So this will be the polarization inside. Okay, so the polarization will be my electric displacement vector minus epsilon naught and the electric field. So this will be rho r over 3 r hat, which is this, minus epsilon naught times this, which is just this one. I end up with this. Okay, and this is where we end up there. Now, you have the electric displacement on the outside, you have the electric displacement, you have the electric field. Calculate the polarization outside the sphere. And I'm going to ask you to do it because you're falling asleep. So this is the equation that you need. Polarization is going to be displacement minus epsilon naught E. Oh, this one. Polarization is going to be displacement minus epsilon naught E. So this is the polarization inside. Now you need on the outside, this is your displacement, your electric displacement, and this is your electric field. So calculate the polarization. But what you got? 0. And you don't even need to calculate anything. The polarization depends on the presence of the material. If there's no material, if you are on free space, there is no polarization. But it's good that the equations actually match that. So I'm going to have rho r cubed over 3r squared minus this times epsilon naught. So I'm going to have epsilon naught rho r cubed over 3 epsilon naught r squared. All this in the r hat. So these are going to cancel and all that's going to be 0. Okay? If you don't have material, there's no polarization. If you don't have I don't know where to put it. But if you don't have that extra material when the molecules are going to align, then that's it. Okay. Now, I'm going to look at my polarization vector. My polarization vector is going to be this guy over here. Okay, this is in the r hat direction. Okay, I'm going to rewrite it here. Okay, and what I'm doing is I'm working with a sphere with a radius r, and this is just a dielectric. Okay. Bless you. Now, I can calculate the bounded charge. The bounded charge inside the volume and in the surface here. Okay, so I'm going to do that. So to calculate the volumetric bounded charge, that's going to be negative the divergence of the polarization. And to calculate the surface bounded charge, that's going to be the polarizations times a normal vector to the surface. Okay, so I want you to calculate the volumetric bounded charge. Okay, now you have to be careful because we're working with the spherical coordinates. So in the spherical coordinates, the divergence of A is going to be 1 over r squared, the partial derivative with respect of r squared AR. Okay, so calculate the bounded volumetric bounded charge. Yeah. So you should got something like, let's see, rho over 1 minus 1 over epsilon r. Yeah? No?
Did you put, is that a mistake that you said PV over VV is negative? Delta.
Negative this.
Okay.
Yeah.
So then that's what, yeah.
Okay. Okay. Is that what you got?
No, I'm just a little lost. It's okay though.
Okay, so let me do it step by step. So what I'm gonna do is I'm gonna apply this to this polarization vector. Okay, so I'm gonna take out all the constants. So I'm gonna have rho over 3, 1 minus 1 over ER. Oh, there's a negative over here. For 1 over R squared. One over R squared, partial derivative with respect to R of R squared, and my AR is just gonna be R. Yeah.
I was confused on the AR part. If I could just put R in that.
So yeah, so this will be my PR. All this is PR.
Oh,
Okay. In this particular case, the polarization doesn't have any components in phi or theta, so it's just gonna be this. And from all this, everything is a constant except the R. So that's what it can get out of the partial derivative. So it will be the derivative of R cubed and this will be just 3R squared over R squared. Yeah. Okay. So if I want to calculate the surface charge, in this case, I will need to look at the surface of the sphere. And in this case, the normal vector, this dot and hat, the normal vector is going to be in the r hat direction. Okay, so if I want to calculate the bounded surface charge, this will be rho r 3 1 minus the r hat dot r hat. Now, this is the surface at a distance r. So in this case, I need to evaluate when r lowercase r is equals to the surface that I'm looking at. So this will be rho r 3 1 minus 1 over er. Okay. Nick, make sense? Okay, so I have an expression for the volume density charge, and I have an expression for the bounded surface charge. Okay, so I can find what is the charge in the volume, and I can find what is the charge at the surface. Okay, so the charge at the volume will be my volume bounded charge times the volume of the sphere. And this surface charge will be the surface charge times the area of the surface. So for the charge of the volume, that will be minus rho, 1 minus ER, and the volume of the sphere is 4/3 of pi capital R cubed. And the surface of the charge is going to be rho R over 3, 1 minus 1 over AR, and the surface, the area of the surface is going to be 4 pi R squared. Okay, if I add them together, I'm going to get 0. Yeah, so we don't have any free charge here. This dielectric is electrical neutral. We have a polarization here, but it's a polarization that exists maybe because the material is naturally polarized. But there's not an extra charge. There's a no free charge. So when you don't have any free charges, the charge on the volume has to be equal to the charge on the surface. Okay, it's like this example that I showed you at the beginning. This material and this material, they have the same charge. The only difference is that when you have the presence of an electric field, this charge, it changes directions, but we're not adding any charge. We don't removing any charge. It's just have the direction. But in this case, and in this case, we have the same number of positive and negative charges. So if I were to add all the negative charges and all the positive charges, here and here will be 0. It's just that here they're oriented, so we have this polarization. So it's the same thing here. We have the same positive charges, same negative charges. It's just that they are oriented, so they're going to create a polarization. Yeah? Is it making sense? Ish?
Yeah, I just don't like that it adds up to 0. It makes sense that it adds up to 0, but
Yeah.
it's like all that writing and just equals 0.
It's not always 0.
Yeah.
We'll make it easy and constant.
Okay. Okay, so we have this sphere or this cavity, and this cavity is inside two different dielectric materials. Okay, and we have some charge. Some charge on the surface of each dielectric. So when R equals 10, we're going to have 4 coulombs, kind of like spread around the surface. And then when R equals B, we're going to have -6. And on the last one, we have 10. And we want to find electric field, electric displacement, and polarization everywhere. So from all these different sections. Okay, I'm gonna do the first one because it's the easiest one. Yeah, so I'm gonna assume when R is inside, when R is less than A. Okay, so the only thing you need to do, calculating the electric field, calculating the electric potential, calculating the polarization is hard if you don't know the electric field. And calculating the electric field is hard because you really don't know the polarization. So the only one that you can trust is the electric displacement. Okay, so I'm gonna be working with electric displacement. So I'm gonna use Gauss law, and I have dot ds equals Q enclosed. So when R equals less than A, what is the charge enclosed? Okay, now 0. So Q enclosed is 0. So the electric displacement is 0. Electric field is going to be 0. And polarization is going to be 0. See, that's what I like to do the first one. Okay, let's try to do the second one. When R is between A and B. So when it's in this red dielectric. So I'm going to have electric displacement dot ds equals the charge enclosed by A. Okay, so the charge enclosed is going to be 4. Okay, because of symmetry, and if you can imagine, my Gaussian surface is a sphere, so this dot ds, that's going to be d times 4 pi r squared. So this one is easy. I'm going to put it over here. So it's going to be 4 over 4 pi r squared. R hat direction. So that's going to be equals to 1 over pi r squared. Okay. Now, the electric field, I know that the electric field is going to be the electric displacement divided by epsilon. So this will be 1 over 2 epsilon pi r square. These two epsilon, that's the electropermittivity of that material. And all these are in the r hat. And the polarization, that's going to be the electric displacement minus epsilon naught times electric field. So that would be 1 over pi r square minus epsilon to epsilon pi r square. And this is 1 over 2 pi r square. Okay? Make sense? Do the last one. Do when R is bigger than C. So you and Jacqueline, is there any other female physics student besides you two?
I don't think in our graduation course,
No, but in general.
I in general, you guys don't
probably.
Yeah.
I think so. I think Serena was the only possible other one, but I don't think she.
She was in engineering, and I don't know if she's gonna stay there or not.
Last time I talked to her, she said after electrical circuit, she didn't want to.
Oh.
I tried helping her a little bit in there, but I don't know how much help I have.
Yeah. So it's only you, Jacqueline, and that's it?
So,
Okay.
Like, well, it's only you two in the whole physics department.
Well, Kelsey, but Kelsey's graduating this year.
yeah.
And also, there's not many guys, like, I mean, there's, in total, there's like,
Yeah, like people getting a physics major.
But when you add physics,
Guys doing physics plus, like getting physics major, probably.
doing physics classes, yes, it's very like male dominated, even the lower levels, like kids just getting credits. But like physics majors, I can't think, I mean, I can think of you and me, Zach,
Zach in physics or is he engineering?
it's physics.
Physics is a
and
Jack. Jack.
I think Stevie's physics.
Is that really it?
Hmm?
Everyone's in engineering, I know.
Yeah, I was gonna say, all the other people I'm thinking of are engineering.
Well, we put them all together.
Oh, yeah.
I mean,
all
there's so
engineering
few
physics.
of us,
Yeah.
so.
Is that really it though? We have like less than 10 people doing physics.
Yeah, and you are a big class.
We're a big class for it.
You are a big class of engineering.
They told me when I came in, they're like, when I first came here for a visit, I think I talked to Jensen on my visit, he's like, we don't have many people, like, your classes are gonna be small as soon as you get to higher levels.
Yeah, Jensen also gave me that thing of like, yeah, once you get beyond intro level stuff, your class size is gonna go.
Yeah. Yeah, so this one, having 6 people here is actually unusual. Yeah. So what you got for D?
Oh, no, I was over C. I was doing between D and C.
No.
If it's over C.
So there's a conference, there's a women in conference, and we usually select students, and that one I think is usually gonna be January or February.
That's what, yeah, Judson told me to sign up for it,
Mhm.
so I did, but I didn't really look much into it, I just kind of turned my application.
Yeah,
Did that, but I don't really know what it is still, or anything else about it.
so it's a regular conference, people go and present work, or you just want to go and make connections, like if you're thinking about going to grad school, that's a good place to go and talk to people. So if you see someone that is doing a research that is kind of interesting, you can go and talk and say like, oh, by the way, I'm graduating. Do you have space for new students? I would like to talk to you more and blah, blah, blah.
Oh, okay.
So that can help you. I think they have job offers too. So it's good to have a couple of presentation cards and a copies of your resume and just send them.
I think Jackie's going, I think that's what she said.
I was like, I asked her if she would, I would go with her, I don't wanna go by myself,
Yeah, usually it's better if you guys go together.
yeah.
Okay, so D, you will get 14 minus 6. That would be no
D, what?
minus 2, 8. So this will be
How did you get 80?
So do this, Q and close, right? When R is bigger than C, it means that R is gonna be over here. So the Q and close will be the Q that I have at A plus the one that I have at C plus the one at B plus the one at C. So that would give me 8. So it's all the charge that you have enclosed in that big Gaussian surface. Okay, what will be your E, your electric field?
E would just be 2 epsilon r squared.
Yeah.
2 pi epsilon r squared. Right? And P?
Nothing.
0. Okay. You know it's gonna be 0 because there's no material. Even if you do D minus epsilon E, if you do it, you will see that you're gonna find this minus epsilon of this is gonna be 0. Okay, is it making more sense?
Yeah, once you, I got 8, but I wasn't really thinking about the Q and close equal to go outside.
Okay.
I've drawn another circle.
I am.
No, like when you put your like pen down, and so you would draw a third circle inside. Draw like another 3 circles.
So let me. We have charge Q right there in the center. Between A and B, we're gonna have a dielectric. And the electropermittivity of this thing is just ER times epsilon naught.
So there's no just space.
No, everywhere else is going to be just empty space. Okay, and I'm going to calculate the polarization between A and B. Okay. Now I know that because of this Q, there's going to be a surface charge here. And there's going to be also a surface charge over there. But again, I cannot calculate the surface charges without getting the polarization. And I cannot calculate the electric field if I don't know the polarization. So the only option that I have is to work with electric displacement. So the electric displacement is going to be equals to the Q enclosed. And this one Q enclosed is a free charge, okay? So even though I'm doing my Gaussian surface around here, I'm just going to look at this Q. So this will be d 4 pi r squared equals Q. So my d is going to be Q over 4 pi r squared. And E will be Q over 4 pi epsilon naught epsilon r squared. Okay, all these in the r hat direction. Okay. The polarization again, going to be d minus epsilon naught E. I'm going to do it a little bit quick. So this is Q 4 pi r squared minus Q 4 pi epsilon r squared r hat. So this is just Q 4 pi r squared 1 minus 1 over epsilon r. Okay. I'm going to calculate the surface charge density. So the surface charge density, that's just going to be the polarization times n hat. Okay. Now I'm going to have two surfaces. So I'm going to have surface A and surface B. So to calculate, who the hell is? To calculate the surface on A, I'm just going to do, this is A and this is B. The normal vector of A is going to be towards the center of the circle. So that's going to be negative r hat. And for B, the normal vector to that surface is going to be pointing out, so that's going to be positive r hat. Okay, so for surface A, this will be q 4 pi a squared 1 minus 1 epsilon r, oh, and this is negative. And for surface B, I'm going to have positive q 4 pi b squared 1 minus 1 er. Okay. And if I want to calculate the volume, bounded volume charge, remember that's going to be minus rho, minus the divergence of P. So that would be minus the divergence of q4 pi r squared. And this thing is okay. And notice how this derivative, this partial derivative, this r cancels with this r, so everything is going to be 0. Okay. So I know that today was kind of intense, but we did all the homework that I was planning for you to leave you for the weekend. So yay. No homework this weekend. I'll give you homework on Monday, Tuesday, Monday. That's it. Have a good weekend. Have a good break. Those of you that can go home. Good luck on your games. And that's it. Take care.